Let's learn about surface tension in this video. You may have noticed water droplets on a surface or clinging on the walls of water bottle appear almost round. And you may have also seen the surface of still water in a glass or container, or perhaps the surface of a lake appear like a stretched transparent sheet. Both of these are due to surface tension of water. Surface tension does not just apply to water. There are other liquids too where you can examine surface tension. Imagine we have water in a glass. Inside the water, a water molecule exerts a resultant pull force on every other molecule up to a very short distance in its vicinity, which is of the order of just a few molecular diameters. So a molecule well inside the water has a zero resultant of this attractive force. But for a molecule on the surface of water, the water is on one side of it, while there are air molecules on the other. This water pulls on the molecule downward, while the air molecules pull upward. But the force by the air molecules is very less than that of the water molecules, and we get an asymmetric force which pulls the molecule downward. By the way, this also applies to all molecules just near the surface, but we consider them as on surface. Now expand this to all the molecules on water surface. We can see that the whole surface is pulled down, and we observe a stretched surface. The water drops also turn spherical due to the same action of pull of surface molecules toward the center. Surface tension can also be explained by the tendency of liquid to decrease its surface area. This is why the surface of water seems stretched, because it's always trying to decrease its surface area and thus in a constant state of stretch. You may also ask why a small drop or soap bubble always turns spherical. That's because for a given volume, a sphere has the least surface area. On a relative note, imagine why almost all astronomical objects are spherical. Thus, mathematically, surface tension is the force per unit length. We have seen that there is a net downward force on the molecules on the surface of liquid. A molecule therefore moves down, and another molecule from inside the liquid takes its place. This new molecule moves against the force on it, and hence work is done on it. This work done is stored in the molecule as energy. Thus the whole surface has energy stored in it, called the surface energy. This surface energy per unit area can also be termed as surface tension. The surface of a liquid always tries to be perpendicular to the net force to minimize the surface energy. Now when a liquid is in contact with a solid surface, the solid surface exerts adhesive force on the liquid molecules in contact, while the liquid as a whole exerts cohesive force. The resultant of these two forces and the weight of the liquid decides the curvature of the liquid. The angle between the tangent to the curvature of the liquid and solid surface is called contact angle, and it comes out to be less than 90 degrees in case of water and greater than 90 degrees in case of mercury. Note that the contact angle can change depending on the nature of solid-liquid pairs, change in temperature, amount of impurity, and medium above the liquid surface. If you have a liquid drop or a bubble, then the pressure inside the drop or bubble is greater than the pressure outside it. Or in case of a curved surface of liquid, the pressure on the concave side is always greater than the pressure on the convex side. If you take a tube of small radius, called a capillary tube, and dip it in a liquid, the liquid rises or drops inside the tube depending upon the liquid's surface tension. Consider this arrangement. When we dip a capillary tube in water, the surface tension causes the water to curve inside the capillary and form a hemispherical shape. The pressure at points B and D must be same for being at the same horizontal level. But point B being on the convex side of the liquid surface in the capillary, the pressure at B is less than that at D. In order to balance the pressure difference between the 2 points, the water rises in the tube by a height h so that the pressure at B now equals the pressure at D. And this side can be calculated by the equation h is equal to 2s cos theta divided by r rho g, where S is the surface tension of the liquid Theta is the contact angle, r is the radius of the capillary tube, rho is the density of liquid, and g is the gravitational acceleration. For mercury, the contact angle is greater than 90 degrees, so cosine of this angle becomes negative, and therefore the height h becomes negative. Negative height just means that the liquid will go down with respect to its original level.